All right. Hi, everyone. Can you all hear me in the back? Cool. My name is Dom Rowan. I'm a fourth-year graduate student at Ohio State. I work with Chris Stanek, Chris Kachanik, and the rest of the Assassin team. And today I'll talk about some of the work we've been doing with Assassin to characterize eclipsing binaries. All right, the big picture, we're all here because we're interested in improving our understanding of stars. We want to develop models of stellar structure and evolution. Sometimes we have to convince our friends in other disciplines this is important, right? For those folks that work on galaxies, we know that we need to understand how stars form, how they fuse new elements, return them into their environment. Or on smaller scales, if we want to characterize exoplanets, we measure planet properties like their size relative to host star properties. So uncertainties in our stellar models translate into uncertainties on planet parameters. And there are a number of physical processes in stars. We've heard about them already this week, like convective overshoot and mixing and rotation that affect the observed properties of stars. And it's important that we make direct comparisons between observations and these stellar models. We need to measure fundamental stellar parameters, namely the mass and the radius, across the Hertzsprung-Russell diagram for stars of different evolutionary state, metallicity, etc. And the best way to measure precise stellar parameters is to use detached eclipsing binaries. The idea is we can take two stars that have evolved effectively in isolation. In their light curves, we measure periodic eclipses. We take spectra, measure the radial velocity orbits of both components. And by combining just these two data sets, we can get a complete picture of both these stars. We can measure both masses and radii without using any stellar models. Right? This is just Kepler's laws and basic geometry here. And this is not a new idea. It's been done for decades. This is probably the premier sample of detached eclipsing binaries from Torres et al. Is about 100 binaries here with masses and radii measured with 3% fractional uncertainties. And these results have been widely used to calibrate other mass estimation methods, to make direct comparisons with stellar models, to characterize exoplanets. And since then, we've continued to observe more detached eclipsing binaries, measure more masses and radii, but we're still sitting at around a few hundred systems with these precise measurements. Now, we're definitely in this era of large all-sky surveys, so we have this opportunity to expand the sample considerably. Pretty much every photometric survey has identified tens of thousands of eclipsing binaries, usually as part of some machine learning search for variable stars. And we all know that the most awesome photometric survey is Assassin, the all-sky automated survey for supernovae. The basic stats for Assassin are up on the screen, but the main idea is that with Assassin, we're observing the entire sky in optical light with daily cadence. We've been doing this for about a decade now. And so this makes Assassin a great tool to study the variable universe. Indeed, there's been more than 400,000 variable stars identified in Assassin. This figure is showing their sky distribution. All the points here are colored by their machine learning classification. And within these catalogs, we have more than 200,000 eclipsing binaries. This not only includes those detached systems that we're interested in for our mass and radius determinations, but also interacting systems, contact binaries, ellipsoidal variables, things like that. And we have the computational tools necessary to characterize these things. We can use tools like Phoebe that create these kind of mesh model grids of stars, allow us to model light curves or radial velocity curves. With these tools, we can do more complex things like consider star spots or pulsations. And we can apply them to all different types of binary stars, all the way from our detached systems to more exotic phenomena like heartbeat stars or binaries with compact objects. And so our goal is to say, let's apply Phoebe on a large scale. Let's model tens of thousands of Assassin eclipsing binaries all at once. I'm going to skip over pretty much everything about how we do that and just show you some light curve results. So this figure is just some example Assassin light curves. The Phoebe models are overplotted in black there. And the main idea is that we're able to model light curves across this different type of morphology, different parts of the parameter space. So for example, one on the top left, right, we have an eccentric system where the eclipses are a bit closer together. We have systems where the fractional radii are larger, right? So we have these wider eclipses. These stars are starting to fill their Roche lobes. So we see this kind of rounded out of eclipse shape. We also have targets where there's a large difference between the effective temperatures of the two stars. So we have one very deep eclipse, one very shallow eclipse. And in total, we have more than 35,000 detached eclipsing binaries with these Phoebe model fits. This is the largest sample by more than an order of magnitude. And what we're actually solving for here is parameters related to the orbit, like the eccentricity, the inclination, as well as parameters related to the stars themselves, namely the ratio of the effective temperatures and the fractional radii. And this means we can start to explore some of the distributions between those parameters. I'll show one example here for time. This figure is showing all of our binaries on the Gaia color magnitude diagram, and the points here are colored by the ratio of the effective temperatures. So those bluer points are systems where there's a large difference in effective temperature. We see those are mostly concentrated on the upper main sequence or below that solid black line that represents a binary isochrone of equal mass. It's fairly intuitive. If you want your binary system to have two stars with a large temperature difference, you need the hot star to be fairly hot, fairly high up the main sequence. This figure is also showing how we kind of divide up the CMD into binaries that have photometric primaries on the main sequence versus subgiants or giants. This is just another way we can kind of tag all of our systems. We also label around 700 systems with additional variability, not just eclipses, but also rotational variability, pulsators, quadruple systems. This is one example of one of those spotted stars. There's about 400 of these in our catalog. In the assassin light curves for these, we often see this kind of long-term modulation, but in the test light curve, which is what I'm showing here, we can really see like the spots evolving on the surfaces of these stars, even within the length of a single test sector. And so you can imagine if we got RVs for these kind of systems, we can simultaneously fit for the masses and the radii of these stars, as well as the star spot parameters, right? We have an independent constraint on the inclination here. And so if you're interested in doing that or anything else related to our assassin binary stars, I'd encourage you to check out our online database. Really, the goal was to say for people that are interested in different types of binaries, how can they identify a sample for their own research interests? So you can search our entire catalog. You can say, okay, I want to look for eccentric subgiants or those binaries with large temperature differences. So you can download our full catalog or the subset based on your search result. You can also check out individual systems, view their light curves, view their Phoebe model fits. All the fit parameters are listed on the page, et cetera. And so we hope this is generally useful for the community. But I want to get back to the main idea, right, which was to measure masses and radii. So far, I've just talked about light curves. We need to add in radial velocities to make these mass and radiation measurements. One way we can approach this is with large spectroscopic surveys like Gaia. The third Gaia data release, which is about 2 years old now, includes more than 5,000 double-line spectroscopic binary orbits. This is exactly what we need to measure masses and radii. This figure is showing the apparent magnitude distribution of that catalog in black compared to our catalog in blue. So the overlap, which is shown in red here, shows that these are really some of the brightest assassin eclipsing binaries, some of the fainter Gaia spectroscopic binaries. But we have about 130 systems to work with here. What we can do is just simultaneously fit the assassin light curve with this Gaia RV orbit model to measure masses and radii. Our results are shown in black. That Torres et al. Catalog I showed back in the introduction is in red in the background there. And so comparatively, we have larger fractional uncertainties, mass errors of around 8%, radius errors of 6%. But I think it's important to remember that what we've done is taken two large publicly available surveys to measure masses and radii on a large scale. And so as the scale, especially of the spectroscopic surveys, expands with future Gaia data releases, with missions like Milky Way Mapper, we can expect to add in hundreds more points to this figure fairly easily. And this is especially important to fill out parts of this parameter space that are relatively sparse, like on the lower main sequence, or I specifically want to emphasize the giant branch. There's only 3 stars that have substantially evolved off the main sequence in that Torres et al. Catalog. We add in 12 here. And there's a number of physical processes in stars like convective overshoot, where it'd be great to have these dynamical mass and radius measurements of red giants. And so to that end, we've continued to observe a number of systems with dedicated spectroscopic follow-up. We've been using APF at Lick Observatory, Pepsi on the LBT, and Chiron on SMARTS to follow up a number of eclipsing red giants identified in Assassin. This figure is showing the 25 targets we've been following up about the past year and a half or so on the CMD. So we just select these based on our photometric primary evolutionary state label I mentioned before. All these are fairly bright, 13th magnitude or so, so they're accessible with our various spectrographs. And the systems are all detached, so periods of 50 days, right? These systems haven't interacted before, but they are probably tidally locked, so rotational variables or rotational velocities of 15 kilometers per second. Now we actually have to do the hard part and measure the radial velocities ourselves. We don't have the spectroscopic survey, automated pipeline stuff. And so we do this with a combination of spectral disentangling and two-dimensional cross-correlation. Okay, so I'll show some RV orbit results. These are 4 targets. The one on the top left, uses APF and Pepsi observations. The other three are all with Chiron. The red and the black curves here are tracing the motions of the primary and the secondary star, right? And you can immediately see that the amplitudes of these curves are about equal. So the majority of our targets are twins. You can also see that most of these are nearly sinusoidal, so almost all of our targets have circular orbits. The obvious counterexample is the one on the lower left. And in general, we only need like 8 to 10 RV observations to get a good constraint on the orbit. We already obviously know the orbital period and the eccentricity from our assassin light curves. Of course, we can take this a step farther, simultaneously fit the assassin light curve with our radial velocity measurements. This is showing one of our Phoebe MCMC results. So these assassin light curves are great. I'm not biased. We have these nice, well-defined eclipses with very precise minima. So this means we can get good constraints on the inclination and on the fractional radii of these stars. When we add in the radial velocities on the right, we can turn those fractional radii into physical radii and measure both masses. The figure on the right is also showing, our RV uncertainties are 100, 200 meters per second or so, but this is totally fine if we're looking at RV amplitudes of tens of kilometers per second. And so this means we can measure pretty precise masses and radii. We definitely hit our goal of 3% fractional uncertainties, less than 1% in some cases. So far, we've done this. We've measured masses and radii for 8 binaries. That's 16 stars. All but one of those has evolved substantially off the main sequence. You can see the one kind of towards the right. One of those stars is still on the main sequence. You also see that most of these stars ended up being fairly massive. We obviously didn't know this when we started spectroscopic follow-up. And as we mentioned before, most of these systems are twins. So it'll be interesting to make direct comparisons next with evolutionary models. So this is the first dedicated spectroscopic survey for these eclipsing red giants in the Milky Way. We're adding in a few more systems later this year. And so stay tuned for that. But with that, I'll stop here and I'm happy to take any questions.
You mentioned both that you have masses. Oh, Fred Adams, Michigan. Can you comment on the twin excess? Do you have enough data to tell us anything about the current status of that?
Yeah, the question was, is it, can you comment on the twin excess? Is that surprising? Yeah, I think it's hard. I wouldn't make a definitive statement on it. Part of it is that we've been following up 25 systems, and these are the first 8. They all ended up being twins. Those are the easiest to measure masses and radii for, because you can see both components so clearly in the spectra. So I don't have a strong comment on that. We have a few systems that aren't equal mass, but when we have the full sample, that's something we can explore.
So I come from this world of astrometry orbit fitting, and where we're measuring fitting proper motion and parallax in orbital parameters, ideally simultaneously. And I've noticed that when we don't, so I'm particularly curious about item 2 up here. When we fit these things not simultaneously, we've noticed that this affects more the orbital motion sessions with the proper motion parallax. It affects some of the orbital parameters more than others. I'm wondering, have you done any tests to see if if you get a similar thing when you have your stinger via orbit, or how it affects it?
So was the question about the parallaxes and those kind of orbital parameters, or the Gaia RV orbit parameters? Okay. So when we fit simultaneously, we can only do this for a subset of our systems. And so maybe the answer is yes, sometimes the Gaia RV orbits are unreliable. For instance, we can directly say, did Gaia get the period correctly or correct based on, we know the period from the assassin light curve. And half the time the answer is no, somewhat surprising. And so, beyond that, we kind of just said, let's just leave, let's take what we can and just leave the rest for later.
Got time for one more short question.
Great talks at Barnes and Noble. I was wondering, at what separation do you expect these stars to no longer affect each other in a way that could influence your interpretation of their observed rate?
Yeah, the question is, what kind of separations do we need? So we're not just worrying about systems that have interacted. Yeah, I think the easiest way to check that is just to look at the light curves, right? You can see, are these stars distorted, right? And these stars, as they're making their first descent, they're just off the main sequence. So we can say, okay, well, they're not interacting as giants. They certainly haven't interacted when they're on the main sequence. And so like typical periods, we have hundreds of days, right? You know, we're looking at longer period systems would be awesome. Those are obviously just harder to find.
Thank all of our speakers.